needed. All right. So when you write down the right profit function, the right utility function, this is the derivative. And so we're going to get y1 star equal to y2 bar plus x divided by 2. Okay? And it's clear from the utility function of player 2 that y2 star equals y1 bar. We don't even have to do calculus on that if you don't want to, because the biggest that the utility function for player 2 can possibly be is when y2 equals y1. Otherwise, it's going to be negative, and it equals 0 when y2 equals y1. Okay, and so now in the second period, they have to play an equilibrium in that subgame. So in equilibrium, y2 star equals y1 star. Okay, and so y1 star equals y1 star plus x divided by 2. And so 2y1 star equals y1 star plus x. And so y1 star equals x. Okay? So that must be true in equilibrium. And that's a much better condition than what I found before, because what I found when I had the wrong profit function in there, what I was finding was that that player 1, his choice of x in the first period was already determined in the second period, which is weird because he didn't optimize that in the first period. But now we're going to be like, okay, he knows that when he goes to the first period, whatever he does in the first period, he knows that he's going to do the exact same thing in the second period. X is player 1's choice in the first period. Y1 is his choice in the second period. And what the subgame perfection tells us is that, hey, in the second period, I have to, I'm going to do exactly whatever I did in the first period. Okay? So we can make that substitution into player 1's profit function, knowing what's going to happen there, and also knowing that y2 star is going to equal x because y2 star is going to equal y1 star. So his utility function in the first period is you're going to make the substitution for both y1 and y2. So it's going to become x squared plus x squared minus x squared minus x to the third over 3. Do you understand?
Yeah, because when we plug it in, it'll be like the same thing. That's why they're squared now.
Yeah. So that's 1x squared plus 1x squared minus 1x squared. So that's going to be just x squared minus x to the third over 3. And so if we take the derivative of utility with respect to x, we're going to get 2x minus 3x over 3, where the x is squared, but the 3's are going to cancel out. So it's minus x squared. Okay? And if we take the first derivative, if we take the derivative of the second, if we take the second derivative, all right, the first derivative of the derivative, we're going to get 2 minus 2x. And so as long as x is big enough, that is still a concave problem. And so let's see if it's concave in the region that we're worried about, like the region of the solution. So we'll set that equal to 0 and call it x star. So that means that, let's see, 2x star minus x squared star equals 0. And so we can divide both sides by x. And so, do it like this. 2 minus x equals 0. and those x's are x stars. And so that has a solution when x equals 0. And it also has a solution when x equals 2. And the solution where x equals 0, the player one's utility is going to equal 0 because everything is going to equal 0. If x is equal 0, y1 is equal 0, y2 is equal 0. And so everything's going to equal 0. When player one chooses 2, then everything in that equation is going to be 2. And so we're going to get the utility is equal to 2 squared, which is 4. And then we're going to get 4, and then we're going to have 2 times 2 times 2, 8 over 3. So utility is going to be 4 minus 8/3, and that's going to be positive. And so the solution to the problem is the x star equals 2, which is good because when we found this derivative over here, when we found this derivative, when it's not concave everywhere, it's only concave as long as 2 minus 2x is greater than 0. I'm sorry, yeah, 2 minus 2x, because that's the second derivative, and that's not true at x equals 0. So the solution that we were interested in is the bigger one anyway. Okay, so yeah, this problem isn't as bad as I made it out to be at the beginning, because I had twice wrote down the wrong utility function, and that'll get you every time. But it's not so bad once we get kind of write the problem correctly down. Again, just like Stackelberg, I mean, so the key thing here is something happens in period 1, and then something happens in period 2. And whatever happens in period 2 in subgame perfect Nash equilibrium has to be solved in equilibrium. So they have to take whatever x is, they take it as given and do the best they can, because it has to be an equilibrium of the subgame. And so taking x as given and then solving y1 and y2 simultaneously, we treat it just like any old Nash equilibrium problem from chapter 9, right? And so we take the derivative for player 1, we have y1 star equals y2 bar plus x over 2. We take the derivative for player 2, or even just look at the profit function and say, okay, y2 has to equal y1. And then we say, okay, in a subgame perfect Nash equilibrium, that subgame is in equilibrium, so y2 star equals y1 star. Solve for that. That tells us that both y1 and y2 have to equal x in the subgame, if that subgame is played in equilibrium. And if the subgame is played in equilibrium, then we go back to the initial game and say, okay, well, the whole game overall has to be played in equilibrium that induces the equilibrium of the subgame. And so we say, okay, well, player 1 now knows that whatever x he chooses, he's going to also choose that same value for y1, and so is player 2 for y2. So substitute that x in everywhere, and now we have a new profit function, all right, the period 1 profit function. Maximize that thing, and that's just a one-dimensional problem. All right, and so we end up with x equals 2, and so the final solution would then be x star equals y1 star equals y2 star equals 2. Everybody's picking 2 for all 3 of the choice variables. But this is a lot like Stackelberg in the sense that in the 2-player game with player 1 moving first, player 2 moving second, we're gonna the game at the second move has to be solved in equilibrium. And so whatever happened in the first game, whatever the in the first step, which was player 1 moving, player 2 treats that choice x1 as given. That choice is given. Let me find x2 best I can. And now player 1 knows what that profit function for player 2 is. Plug that profit function into her utility function, her profit function, and then find the best response to that. And that's exactly what we've done here. where in the second period, player 1 and player 2 simultaneously solve that Nash equilibrium. That determines the profit function in the second period. Player 1 takes that profit function, plugs it into first period profit function, and then maximizes. So it's the same process. Questions about this one?
No questions.
All right, cool. Okay, and now let's see. You could either look at one of the other questions, or we can look at Stackelberg and just change the demand function and solve for it. Although I can't promise the algebra will work out prettily because I haven't worked it out ahead of time. But we can do a different Stackelberg question and just change the demand curve, or we can answer one of the other questions. Which one would you rather do?
So, how the question that you're gonna make for us, is it gonna be a weird Nash equilibrium, or is it gonna be like a Nash equilibrium like
It
this?
could be it could be either way. Like, I mean, this question wasn't so weird. Once I mean, it would definitely be one of the hard questions on the exam. Like, there won't, very few questions would be of this level, and I won't know in advance what chapters the harder questions will be from. But it could go either way. It could be a problem like this one that's like using the same ideas but like in a different setup, or it could be a more conventional Stackelberg. So it could be either way.
Is it okay if we change the numbers and see?
Yeah. Yep. So let's say we have a demand curve. Make them symmetric. Maybe P equals 60 minus 2 times total quantity, which means that P equals 60 minus 2Q1 minus 2Q2. All right. No cost.
Is there any bounds?
What's that?
Is there any bounds?
Any bounds? In this case, neither. So Q1 and Q2 are going to be in the range of 0 to 30.
Okay.
Because player 1 is never going to want to choose a number bigger than 30, because even if player 2 chooses 0, he won't go over 30. Same with player 2. Okay. And so player 2, where player 1 moves first. So that means that we start in the second period. We start with player 2, and we say, we'll set up a profit function. Profit for player 2 is going to equal price times quantity. So 60 minus 2Q1 minus 2Q2 times Q2, which is 60 times Q2 minus 2Q1 Q2 minus 2Q2 squared. We take that derivative for player 2, and we get 60 minus 2Q1 bar, belief about what Q1 is. Oh, no, it's not a belief. We actually know what Q1 is because we're moving, player 2 moves in the second period. So it's just a number. It's a parameter at this point, like, because it's already done. Minus 4Q2, set that equal to 0. In this case, that's definitely going, the second derivative is definitely going to be negative. So we can call that Q2 star. And so we're going to get 4Q2 star equals 60 minus 2q1. And so q2 star equals 60 divided by 4, so 7.5. No. 60 divided by 4, geez. 15. 15 minus 1/2 q1. Okay? So that's the profit for player 2. Sorry, the best response of player 2. So no matter what player 1 does in subgame perfect Nash equilibrium, this is what player 2 has to do. Player 1 knows that this is what player 1 has to do. So player 1's profit function is going to take that into account. So player 1, the profit function is going to be set up similarly, 60. Well, in fact, we can already write it out as we did for player 2 because it's the same, but with the q1 and q2 reversed. So player 1's profit function is going to be 60 times q1 minus 2q1 q2 minus 2q1 squared. Okay, so that's just we haven't done any substituting yet. That's just price times quantity. And now we're going to substitute the profit function for player 2, the best response function, into the profit function for player 1. So we get 60 q1 minus 2q1 times q2 minus 2q1 squared. And we'll expand this one out. So that's minus 30 q1. And that's minus or plus q1 squared minus 2q1 squared. Just making sure I didn't make any mistakes there. I think that looks good. And so it's going to equal, 30 q1 minus q1 squared. Okay? And so we take the derivative of that with respect to q1, which equals 30 minus 2q1. Make that a star, set it equal to 0. And so we get q1 star equals 15. And then that means that q2 star equals 7.5. Okay? And so that's going to be the subgame perfect Nash equilibrium of this Stackelberg game. And another equilibrium would be for player 1 to threaten. So another Nash equilibrium, not SPNE, is q1 star equals 30 if q2 greater than 0, q1 star equals 15 if q2 equals 0, q2 star equals 0. So that's a Nash equilibrium that's not subgame perfect. Player 2 is going to choose 0. Player 1 is going to choose 15, which is the best response to player 2 picking 0. And player 2's is the best response because if player 2 picks any other number, not 30, sorry. He doesn't pick 30, he picks 30 minus q2. All right, because if player 1 picks 30 minus q2, both of their profit is equal to 0. And so given that strategy for player 1, firm 2's profit is always 0, so picking q2 equals 0 is the best response. And given that best response, player 1's best response is 15. So this is an equilibrium, but it's not subgame perfect because if player 2 would actually pick 7.5, Oh, I reversed them. Yeah. Q2 equals 30 minus Q1 if Q1 is greater than 0. Q2 equals 15 if Q1 equals 0. Q1 equals 0. So player 2 is threatening player 1 that player 1, if you do anything other than 0 in this game, I am going to pick 30 minus Q1, which will give you a profit of 0. And if you pick 0, I'm going to pick 15, which maximizes my profit. Firm 1 believes him, so firm 1 picks 0. So this is the not subgame perfect Nash equilibrium. Okay? Follow?
So the Stackelberg, we plug into each other to find the Nash equilibrium for like the
Well, I mean, again, so you have to solve the second mover's best response function first, plug that best response function into player 1's profit, into the first mover's profit function, and then take the derivative to find the first player's best response function. Yeah, you're plugging one into the other, but make sure you're careful about what you're plugging into what.
So we always have to solve for player 2's profit first.
Correct. And that's what we did on the last game, in the sense that, well, the choice of Y1 and Y2 happens in the second round, so you have to solve for them first. And we found that for them to be in equilibrium in the second round, you need Y1 star equal Y2 star equal X. Player 1 knows that going into the first round, so plug that into his profit function. Now find the best response function for player 1. So we're doing the exact same thing here. You're solving for the second round first, plugging that solution into the profit function for the first round, and then differentiating the profit function for the first round. All right, make sense?
Yeah, will you label the question like Stackelberg duopoly and then the Corno one, Corno?
I mean, probably not. I mean, I'll probably just describe the game. So I'll probably describe the game as I could even give you a Cornell and Stackelberg with the same description. There's two firms. They face a demand curve. They have no cost. If they move simultaneously, what is their equilibrium quantities? If player 1 moves first and then player 2, what is their what is their subgame perfect Nash equilibrium quantities? Tell me another equilibrium that's not subgame perfect. So I would give you a question like that most likely. If I gave you a Stackelberg, I'd probably just piggyback it onto a Cornell question, but I probably wouldn't use the word Stackelberg or Cornell in the question itself. I just described the environment. All right. So I see there's a couple other people now. Anyone have questions on end of chapter questions or otherwise?
Hi, Professor. This is
Hi.
Nan.
Hi, Nan.
Hi. So, I have I have question about some games in this chapter. I feel
Okay.
like some of them are really big.
Are really what?
Really big.
Yeah. True.
Yeah, like for example, 1B, like part B in question number 1.
Okay.
I feel like does player 1 have 32 strategies?
So no.
Oh,
But
okay.
no. So 1B, so chapter 15, 1B. The game is player 1 chooses out or in. If he chooses out, the game is over. Two
Oh,
are the payoffs. Because there's
ex,
yeah.
excuse me,
Yeah.
Professor. I think you wrote is 1C.
Oh, 1C. I see. I'm sorry.
Yeah.
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 Okay. Yeah.
Mhm.
Okay. One in 1B. So yeah, player one's strategy space. So there's 5 information sets. Each is 2. So it's 2 to the 5th is the size of player one's strategy space, and player two's is 4.
Yeah.
So yeah, it's 2 to the 5th by 4.
Yeah.
So what's it,
So
32 by 4?
Yeah, 32 by 4.
Yeah,
Such a
so that
really big game.
it is a big game. So and so yeah, to put that into the strategic form, if I asked you to put that into the strategic form, it would be a really, really big game for a page, right?
Yeah.
So in general, I tend to try to keep the size of a game that I'd ask you to put into strategic form to like 12 or 16 at the most. But I mean, it's plausible that I could give something like this, although not very likely. And also for a game like this, player one has no ties and player two has no ties. And so that game has unique subgame perfect Nash equilibrium. So there could be a whole bunch of Nash equilibria, pure strategy equilibria, but this game is really, really simple to solve for a subgame perfect Nash equilibrium. So I probably wouldn't spend a lot of time just in the setup of a game like that, because it's not a very interesting game from subgame perspective. So
Yeah, I just feel like this is a really, really big game. So I just want to double check with you. Does player one has
yeah, a game
strategies.
like this, what we would typically only focus on subgame perfect. So I could give you a game like this and I'd say, okay, solve for the subgame perfect Nash equilibria. I am very unlikely to give you a game like this and say, put it into the strategic form.
Okay, got you. Because I also found like question number 3 and question number 11 are also such big games.
Yeah, question 3. Yeah, that one again. It's a game of complete information, and I don't see any ties. There are no ties, so that should have a unique. Unless I'm missing a tie, that'll have a unique. So all perfect information games that don't have ties for any player's payoffs along the chain is unique. And so yeah, actually putting that game into the strategic form, they're 1, 2, 3, 4. Yeah, it's 2 to the 5th for player one, and it's a 4 for player two again. So it's the same size as the last one. And I'm not going to make you put something like that into a matrix. It's it's too much. Yeah, and same with 11. Although I think in 11, no, it's not true. I thought maybe in 11 there was some ties, but there's not ties for player one or player two. So that one's uniquely solvable as well.
Okay.
The problem with perfect information games is if there's a tie for payoffs, you can have multiple subgame perfect Nash equilibria, because you will have multiple, or you can have multiple, because one of the players is indifferent between what they're doing. So it's potential to have multiple subgame perfect Nash equilibria, because in some information sets a player is indifferent between what she does, so she could do either one of them. And so that's possible to induce multiple subgame perfect. So you have to be careful with the uniqueness on games of perfect information, but yeah, in general, I won't make you put games like that into a matrix.
Okay, got you. Yeah, because I feel like I just taught myself like just the game has so many strategies.
Yeah, it would take too long. We'll just if I give you a game like those, a big complete information game, I'm just going to ask you to find the SPNE.
Okay, gotcha. I will try them later. Yeah,
okay.
And I have not yet finished all the questions, so this is all my question, because I also watched the video about question number 2. That was really helpful.
Yeah, the question number 2 tells you a lot. So I think question number 2, and then Stackelberg and Stackelberg-like questions. That gives you
Mhm.
pretty much everything you need for this chapter as far as what I'm going to ask. Like if you can handle question 2 and questions like them, because there's some intricacies on those questions that are challenging.
Mhm.
And the question, the Stackelberg question I just solved, and then we looked earlier at question number 9, which is the
Mhm.
Stackelberg-like question. If you can handle questions like that and question 2, you should be fine.
Okay, okay, got you. Thank you so much.
Uh-huh.
Okay, thank you. That's all my questions.
All right, cool. Anyone,
Mhm.
anyone else? Other questions?
Okay, so I have a question. Can you go over questions on the midterm?
Yeah. Like what question?
Specifically number 8 and 9.
Midterm. Okay. So we have question 8 and 9. So we have a demand curve which has price equal to 170 minus 3 times Q. And each firm has a marginal cost C equal to $20. And if there's only one firm in the market, what's optimal output? If there are 4 firms in the market, what's the Nash equilibrium output? And then what price is okay, cool. So in general, the way you solve problems like this is for player I, we're going to say player I's profit function. I mean, there's 2 ways to solve it. One, you can just take the formulas for Nash equilibrium and for monopoly and best all that stuff. I don't remember what the formulas are. So I have to solve them this way, like to actually solve the problem each time. But it's probably worth doing that anyway. So we have player I's profit function is 170 minus 3 times Q times his own quantity minus C times QI. So that's the first part is total revenue. And this part is total cost. All right, so that's the profit. And we know that the total quantity in the market, the total quantity in the market is equal to 3 times QI plus Q minus I. And then we do that whole thing times QI minus C QI. And this step here is recognition of the fact that the total quantity in the market is equal to the quantity of any one firm plus the quantity of all the other firms. All firms except I. Okay? So I'm just taking that profit function above and I'm substituting for the total quantity in the market. I'm acknowledging that, well, part of that is from firm I and the rest of it is from all the other firms. All right, does that make sense?
Yes.
Okay, and so now I have profit equal to 170 times QI. I'm just multiplying it through by that QI and minus 3 QI squared minus 3 Q minus I times my own quantity minus C QI. All right, that's firm I's profit function for any firm I. It doesn't matter if there's 1 firm, 10 firms. This is any firm's individual profit function. Okay, she forms a belief about what the other firms are going to do and then takes the derivative of profit with respect to her own quantity. And so that equals 170 minus 6 QI minus 3 Q minus I, and that's going to be a belief. We'll call it bar minus C. If we take the second derivative, it's going to equal -6. And so we know that this profit function is concave. So we can take the first derivative, set it equal to 0, and that gives us our optimal quantity. And so our optimal quantity, 6qi, is going to equal the left-hand side of the equation. I'm going to add 6qi to both sides, and then I'll divide by 6. So I'm going to have qi star is equal to 170 over 6 minus 3 over 6, which is 1/2, q minus I bar minus C. Okay. 170 over 6 is 250. Did I make a mistake somewhere?
Do you have to plug in anything like with the cost, or do you leave that out?
The cost is in there, so I have the minus C times QI. I'm just wondering if because I think I made it. I think it was supposed to be. I think it's supposed to be 175.
I think you're missing the see where that before the derivative is supposed to be minus 20 qi.
Oh, C is minus 20.
Yeah.
Oh, that's right. And then I would have had to divide that by I see. So I was good. I was okay up to that point. So no mistakes earlier. That C is equal to 20. And so so I can subtract that from over. So we have 150 minus 6qi star minus 3q minus I bar equals 0. And so qi star equals 150 over 6 minus 3 over 6q minus I bar. And so qi star equals 150 divided by 6 is 25. That looks better. 25 minus 1/2 q minus I bar. So player I forms a belief about what the total quantity in the market is for everyone else but herself. She divides that by 2, subtracts it from 25, and that's her own best response. So the answer to number 8 is, well, if you're a monopolist, your belief about what everyone else in the market does is 0 because there is nobody else in the market. So your optimal quantity is 25 units.
If there was no monopoly, what would
Yes.
the answer be technically?
What do you mean if there was no monopoly?
Yeah, if there was more than one firm, how would you solve the question?
Well, so that's number 9. So that now there's more than, so for question 8, n is equal to 1, and now we're saying, okay, there's more than one firm. How do you solve this? Okay, and so we solve that by saying, let's go to the next page. So we know that firm I's profit function is 25 minus 1/2 times the quantity of everyone else in belief. In Nash equilibrium, Q star, the total quantity in the market for everyone, is just equal to n times the individual quantities. Everyone's going to do the same thing. Okay? And so that equals firm I's output by itself plus n minus 1 times the individual outputs of everyone else, because everyone's going to do the same thing. everyone has same profit function, so does the same thing. So you have everyone doing the same thing, and so I know that my own optimal quantity is 25 minus 1/2 times the quantity of everyone else, but I know the quantity of everyone else is n minus 1 times what I do. Okay? And so now the equilibrium quantity is to just solve for what do I do. And so we could say, well, that's qi star plus 1/2 n minus 1 times qi star is equal to 25. So I have, just making sure I've been susceptible to mistakes today. So that gives me 3/2 times n minus 1 qi star is equal to 25. Yep. And so qi star is equal to, that's going to be 50/3 times n minus 1. Okay, and so if there's 2 firms in the market, the output of each firm is 50 divided by 3. If there's 3 firms in the market, the output of each individual firm is 50/6, right? And so we as we add more firms, the output of each individual firm is shrinking, but the total quantity of market is increasing. So because it's going to be n times this amount. Okay. Although that also feels like I made a mistake somewhere.
I think you plugged something in wrong.
Yeah, it doesn't feel right. So let's see.
Q.
Go ahead.
So it would be qi star equals 25 minus half multiplied by 3qi squared, and then you get 5 over 2 qi to qi star equals 25, and then you just divide that out and it'll be qi star equals 10.
Is this step okay? This first step?
Yeah, that first step is
we're good there. And then the second step,
you should plug in 4.
Wait, we could plug in 4. I'm just I was trying to keep it as a general solution to start. So like as a general thing, I'm just adding 1/2 times n minus 1 times qi star. So that should be okay.
I think this last step is something wrong with it because this one is right.
Yeah, I think so. I think I'm good up to that point. And so let's see. I can say, well, n minus 1 times qi star is equal to 50/3. Yeah. Weird. Sorry. So one more time. Q minus I bar has to equal the sum of the rest of the firms, n minus 1 times qi star. So this first step should be okay. And so yeah. So then we add to both sides. That is fine. Yeah, I'm having a hard time seeing where our mistake is, but it doesn't feel
Professor?
Yes.
Can you go over how you went to the second line to the third line? Because I'm a little bit confused on how you got there. Like where did it?
You mean so from this line to the next one?
From where you from the two, I meant the 3 seconds from that line and the one before, because I don't know how you jumped from that
Oh,
line.
okay. So I have so I can put so this is equal to 2 over 2 qi star plus n minus 1 qi star over 2. And so this is equal to, and maybe this is 5. Okay, yeah, that's where, yeah, I saw this. I saw the chat method. I think that's messaged. I think that's where my mistake was. So now we have 2. Oops. That equals 25. And so now we have 2 qi star plus n qi star minus qi star over 2 equals 25. And so that's going to be qi star plus n qi star divided by 2 equals 25. Well, I can make that a 50 on the right-hand side. And so I'm going to get 1 plus n times qi star equals 50. And so qi star equals 50 over 1 plus n. Much better. So yeah, so the mistake was in my algebra. I was trying to do too many steps at one time and ended up with a 3 halves instead of a 5 halves. But this is just taking my time a little bit more. And so this is going to be the Nash equilibrium quantity, no matter how many firms there are. So it's so if there's only one firm in the market, monopoly, again, we confirm that the total quantity is 25 from the monopolist. If there's 2 firms in the market, it's 50 over 3. If there's 3 firms in the market, it's 50 over 4. And so there's 4 firms in the market. So for question 9, we have qi star equals 50 over 1 plus 4, which equals 10. Okay. Yeah, for some reason my algebra has just been off today. So I messed up that third step. Tried to combine too many steps at one time and had a error in the fraction. Okay, but that's how. So there are equations from the book, not from the book, from the lecture notes where I tell you like what the best response function is as a function of the total quantity of the other firms in the market. And then I gave you a form. So basically, I have the best response function as a function of q bar minus I, and then the equilibrium function as a function of n, the number of firms. And then also for both of them, you have the parameters. So whatever your slope is, whatever your y-intercept is, and whatever your cost is, those variables are m, c, and b. In this case, m is minus 1/2 or 1/2. I think I kept it as a minus. And then we have b is 25 and c is 20. So you do have equations for these problems for question 8 and question 9, where you can just plug, if you know what b, m, c, and n are, or b, m, c, and q minus I bar are, you can plug those into the equations and just solve for them. But I usually start from scratch when I do them because I don't have a good memory for equations.
Okay.
Cool. All right. Sorry about the algebra mistake. Other questions?
For exercise 6, there's 3 players. How would I was able to put it in the extensive form, but I don't know. Should I there a way
Exercise 6 in chapter 15.
Yeah, that goes back to chapter 7, exercise 4, the payoffs.
Right. Let's see.
So how do you put this? Do you need the strategic form to like answer all the questions? Because I don't know how.
It can help. So let's see. Question 7. exercise 4. Oops, sorry. I just lost my. Okay, here we go. So we have I'm just going to let them be R instead, because that's just a lot of R, C. They can choose 6 or 7, 6 or 7, and then the payoffs are 14, 24, 32, 30, 16, 24, 8, 30, 27, 13, 12, 50, and then we have R and C, same time slots, different payoffs. Oops, I made a mistake there. I don't want to start off a game with the wrong payoffs again. 30, 16, 24. And 14, 24, 32. And so M makes a move, and if M chooses a 6 o'clock time slot, the payoffs are the left matrix, and if M chooses the 7 o'clock time slot, the payoffs are the right matrix. And so let's see, in question, what is this? Question 6. We're oh, that's so the variation is first M chooses the time slot, then after observing the choice, R decides, and then C decides. So it's the same, the game has the same payoffs. It's just that instead of a simultaneous move game, which might provide for many equilibria, we're moving sequentially. And so the order is M chooses first, then R, and then C. Okay.
Draw the extensive form game. It's gonna be dotted lines, right?
Can you say it again?
Will it be dotted lines between R's choices and C's choices?
I see. You're thinking about putting this into the extensive form. I see. So there won't be dotted lines because the players will know what each other have done. So C is going to get to see what R has done before R has moved. So M will move first, 6, 7, and now R is going to get to move, having seen what M does. And if M is chosen 6, we're on the left matrix, and so R is going to pick 6 or 7. And if he picks 6 or 7, then C is going to pick 6 or 7, but C is going to see everything that's happened coming forward. Okay, So we could, so basically, and then the same thing down here. It's not a 6 up there, it's a C. Okay, and so this extensive form, if we drew a dashed line through all of C's nodes and for the 2 R nodes, then we'd be back into the game of simultaneous move, right? Where you don't get to know ahead of time. But here, because like we don't have dashed lines because every player knows where they're at because the game is sequential, right? Does that make sense? So there's no dashed lines?
Yeah, that
That's
makes
that's the critical insight here, because now that you see that, now we can just write the payoffs for each one of those branches, and then player C solves by backward induction what her action is at each of those information sets, and then we back our way through. So the problem is pretty straightforward once we're there. So we have what, 14, 24, 32. Just make sure I get them in the right spot. 8, 30, 27. 30, 16, 24, 13, 12, 50. And then we move down. We have 16, 24, 30. 30, 16, 24, 30, 23, 14, and 14, 24, 32. And now we can just go through and see what player 3's best responses are. So she's going to want to pick 6 there. Is that really a 50? Yeah. So pick this one, pick this one, and pick this one. And now R gets to move going backwards. So she knows that if she chooses 6, she gets a payoff of 24, and 7, she gets a payoff of 12. So she's going to pick 6. And then at the bottom one, she gets 24 versus 24. Of course she does. So those are both best responses. And then for M, on the top, she knows what she's getting. She's either getting a 13 or a 14. So she's definitely going to pick the 6 o'clock time slot. Oh, what am I doing? Sorry. We have to compare that to the bottom one. So she knows this top part. M gets what do we say? 14 for sure. So if she picks the 6 o'clock time slot, she's definitely getting 14. If she picks the 7 o'clock time slot, if the other players are playing 6-6, she's going to get 16. And otherwise, if player R goes 7, then she's going to get 14. And so
she would
14.
choose 7.
Well, so one equilibrium. So picking 7 while the other 2 players play 6 and 6 is a subgame perfect Nash equilibrium, right? Because it's if player 1 picks 7, she's and player 2 plays 6. That's a best response to player C playing 6. So everyone's doing a best response. But it could also be the case that she picks 7 and the other 2 players do 7-7. Because picking 7 is still a best response if the other players are picking 7 and 7, because her payoff there is the same is the same as the payoff she'd get by playing 6. So she's indifferent. The 14 at the bottom, 14 at the top, it doesn't matter. And then also picking 6 when the other 2 players are picking 7 is also a subgame perfect Nash equilibrium. So these are all of the pure strategy subgame perfect Nash equilibria. And then, of course, she could also be willing to mix in any proportion between 6 and 7. Player M could be willing to mix in any proportion between 6 and 7 as long as they're playing the 7-7 equilibrium at the bottom. And then there's another equilibrium where if player R in the bottom is mixing between 6 and 7. Oh, wait a second. Oh yeah, player R is mixing between 6 and 7. That's going to induce a mixture between player 1 choosing 6 or 7, but that mixture is definitely going to give player M a higher payoff than choosing 6 above. So there's another so there's two types of mixed strategy equilibria. One is where player M chooses 7, and the other two and 2 mixes R and C, and player C mixes not R and C, 6 and 7. And then we also said that there was the one where player 1 mixes and players 2 and 3, or R and C, play 7-7. Okay.
Good. I missed what when you were talking about 6-7-7.
Uh-huh.
But player R doesn't choose 7 when you choose 6.
Sorry. I meant 7 down there. Yeah, these are shorthand. So a strategy for C has to have 4 parts to it. So I was just pointing out strategies. So I mean it's a bad shorthand that I wrote. I was just pointing out strategies along the path of play. But yeah, that would induce that. So so the equilibria that you're talking about, this one is really, we would write it as player 1 picks 6, player 2 picks 6 in the top one and 7 in the bottom one. And then player 3 picks 6 in the top one, 7, 6, 7. So this is what I meant there. So player 1 is allowed to pick 6. The key is that player R is picking 7 in that information set. So basically, like, player C is always locked into her choice, like every single one, like there's no discretion. And player 2 is able to, I'm sorry, player R is not locked into the bottom one. She's able to pick either one because she's indifferent between the two. And so, yeah, I should have written those out. She's picking 7 at the bottom. And so, yeah, this first one is player 1 picking 7. And then we have, if player 1 picks 7, player 2 picking 6, 6. And player 3 picking 6, 7, 6, 7. And then this one, and then for player 1 picks 7, player 2 picks 6, 7, and player 3 picks 6, 7, 6, 7. Okay. So I mean, it's a strategy is a complete contingent plan. So I was just pointing out particular information sets, but it was ambiguous when I wrote them out, which ones I was picking. So is that more clear?
So it will be M picks 6, and then it will be R picks 6 or 7, and then
R picks 6 if player 1 picks 6. R picks 7 if player 1 picks 7. That's the strategy of player R.
And then for C, it will be if you play 6, I play 6 or 7, and then if you play 7, I play 6 or 7.
Yeah, like so it's if I'm in the top information set. So if 6, 6, I pick 6. If 6, 7, I pick 7. If 7, 6, I pick 6. If 7, 7, I pick 7.
Okay.
So a strategy is you have to tell me what you're going to do at every information set, and so that's what player 2 strategy is always fixed in that way. Like she's always going to, because she gets to see where she's at in the game.
And these are the 3 sub-game perfect Nash equilibriums.
Yeah, these are the 3 pure strategy subgame perfect Nash equilibria, and this one here isn't that one's not one, but this one is. Player 1 could mix between 6 and 7. The reason the top one is not the one that I wrote down is because they get to see what player 1 did, so they don't see a mixture; they only see what the player did. And so the strategies for those guys stay the same. Player 1 could mix between 6 or 7 because as long as player R is playing 7 in the bottom information set. So this one, what I'm saying is player 1 can do any mixture of 6 and 7, provided that player 2 strategy is 6, 7, and player 3 strategy is 6, 7, 6, 7. Player 1 can do anything she wants because she's indifferent between 6 and 7 when player 2 is playing 7 in the bottom information set.
So there's 4 pure.
Well, there's 3 pure strategy Nash equilibria, and then there's 1 mixed strategy subgame perfect Nash equilibria that has player 1 mixing between 6 and 7, and player 2 choosing 6, 7, and player 3 doing what player 3 always does.
How did you get to this mix?
Because if player R is playing 6 in the top and 7 in the bottom, player 1's getting a payoff of 14. It doesn't matter if it's top or bottom, she's getting 14. So player 1 could choose any mixture of 6 and 7, and her payoff doesn't change. Right?
Yeah.
So we have this payoff here, and we have this payoff here. And so if this subgame is played in 6-6, which it always is, if this bottom subgame is played in 7-7, then player 1 is indifferent between 6 and 7, so she's allowed to mix between them. But player 2's strategies stay the same and player 3 stay the same because she gets to observe what player 1 did. So it doesn't matter if player 1's mixing or not. Player 2 says, okay, if you went up, I choose 6. If you choose down, I choose 7. So there's 3 pure strategy subgame perfect Nash equilibria, and there's one mixed strategy, one set of mixed strategy equilibria where player 2 and 3 are fixed, but player 1 is mixing any proportion between 6 and 7.
So would it be the same if I wrote 6 and 7 instead of mix, or I have to write mix?
Well, you could say, the mix is shorthand for, sigma 1 equals P 1 minus P for P in the 0-1 interval.
So
So I'm just saying player 1 can choose sigma 1 equal to P 1 minus P for any value of P between 0 and 1, that's an equilibrium. So for mix, just substitute mix, just put sigma 1 in there, and then below say what must be true of sigma 1.
would that be that P has to be within 0 and 1?
Yeah. I mean, it could be either end. So, I mean, to kind of put a small, like a point on it, but I mean, it really doesn't, this is not important, but so there's 2 equilibria. There's 2 pure strategy equilibria. This one up here and this one up here, that you notice player 2 is playing 6 and 7. Player 1 could choose 7, or player 1 could choose 6, or player 1 could choose a mixture in between the 2. Player 1 can mix any mixture between 6 and 7. So really what you could do is say, here's one pure strategy equilibria, 7 for player 1, 6, 6 for player 2, 6, 7, 6, 7 for player 3. And then there's this other equilibria, sigma 1, comma, 6, 7, comma, 6, 7, 6, 7 for player 3. And sigma 1 anywhere between P is 0 to 1 is fine. And so when P equals 0, we're in the 1 pure strategy equilibria. When P equals 1, we're in the other one. And when P is between 0 and 1, we have a mixture between those 2. So you could really kind of summarize the output of the subgame perfect of the equilibrium of the game is you have this one, and then you have this one. And the other 2 that we solved for up top, this one and this one, are special cases of this bottom one where P equals 1 or P equals 0. So you would really only have to have this equilibrium up here and then this equilibrium here, which includes the other 2 pure strategy as corner cases. I mean, the most important thing is just seeing that there's 3 pure strategy equilibria, and then recognizing that for 2 of them, she is indifferent, so she could mix anywhere between 6 and 7. All right?
Yes, that makes sense.
All right, cool. All right, well, I think we're out of time, but just kind of any other questions you have from this, the chapter or other chapters, just pop back in on Wednesday, and we can work through those. All right.
Okay. Are you gonna have office hour next Monday too?
I can do that.
Okay. Thank you.
All right. Bye-bye.
Thank you so much.